Hello and welcome to episode 2 of my series on contour integration. In this episode we're going to be looking at something called the ML inequality. Before we do that we have to prove a lemma which we'll call the triangle inequality for complex integrands. So here we're looking at a function f which goes from the reals to the complex numbers. And this is the statement. So a and b are real numbers, and f just maps from a to b, it goes to the complex numbers. So in the real case, this is something that you'll have seen in real analysis. It's quite simple to prove. There's a little bit more work to do here. So what we're going to do first is just call this integral something. So let's say we'll just call this alpha here, which we can split up into a real and an imaginary part, which is going to be useful. So whenever we're dealing with the size of a complex number, it's sometimes helpful to look at the size squared, because then we can break it down into the components squared. So the absolute value of alpha squared is the absolute value of alpha 1 squared plus alpha 2 squared. Now what we're going to do is use the fact that alpha 1 is the real part of this integral and alpha 2 is the complex part. So that's going to give us our next step, which is alpha 1 times by the integral from a to b of the real part of f of t dt plus alpha 2 times by the integral of the complex part, the imaginary part, dt. And we're going to write this in quite a special way. So we're going to write this as the dot product of alpha 1, alpha 2 with real part of f of t and the integral of the whole thing. And the reason for doing that is we know that with the dot product there are some inequalities we can start to use. Now you can check that this all works out. So all it's saying is that you have alpha 1 times by the real part plus alpha 2 times by the imaginary part, which is exactly the same as what you have here, and it's all put into one integral. So by the Cauchy-Schwarz inequality, we can write this as less than or equal to AB times by the size of alpha 1 for 2, size of the real part of f of t, the imaginary part of f of t. And by the definition of absolute value of a complex number, this is just the size of alpha times by the size of f of t dt. So what does that give us? That gives us that alpha squared is less than or equal to the absolute value of alpha times by the integral of ab of the absolute value of f of t dt. And then so we can divide through by alpha, which we said isn't 0, which isn't 0. If it is 0, then everything checks out anyway. So we'll say it's not 0. And we'll say that based off what we defined alpha to be, gives us AB t dt is less than or equal to integral of the absolute value, just like we wanted. Okay, so armed with this knowledge, we can go on to do the ML inequality itself, which will be quite a bit easier now. So what does the ML inequality state? If we have some function that goes from a contour gamma to the complex numbers, and this is a bounded function, so for any z on your contour, the maximum of f of z, of the absolute value of f of z, is m. So this is a bounded function. F of z is always less than or equal to m. And we'll say that this gamma is represented by some map, little gamma, from a to b to the complex plane. So if you recall from episode 1, this is how we set up a contour integral. So then we look at the absolute value of the integral over gamma of f of z dz. And from last episode, we can write that as equal to the absolute value of ab, f of gamma of t, gamma dash t, dt. And using the triangle inequality that we just proved, we say that's less than or equal to the integral from a to b of the absolute value of f of gamma of t times by the absolute value of gamma of t, gamma dash of t, all dt. And so from earlier, we know that gamma of t, because it's in gamma, is going to give us this whole thing being less than m times by the integral ab gamma dash of t dt. And if you know how arc lengths work and how the length of a curve works, you can actually see that this is equal to ml, where L equals length gamma. So the whole ML quantity states that the integral over gamma of f of z dz, if you take the absolute value of that, it's less than or equal to ml, where m is the maximum of your function, of the absolute value of your function, and L is the length of the contour you're integrating over. In the next episode, we will look at the fundamental theorem of complex integration, and that is going to be really important going forward.